Welcome again to Chemcrackers. Today we're continuing our series on the mole concept. Now, today we're looking at the mole and masses. Now, in chemistry, there are two mass scales. There is the relative mass scale and there is the absolute mass scale. Now, why do we have such a situation? Now, as the scientists began to discover more and more atoms and began to use different techniques like mass spectrometry to measure their weights, they realized that these weights were so small that it was impractical for most humans to think and work with them in everyday. So for example, the mass of a hydrogen atom is actually 1.674 times 10 to the minus 24 grams. That's very, very, very small. How could we work with that? So scientists began to realize that they had to develop a different scheme of working with the masses of these atoms. So instead of comparing them to bulk objects, they decided to compare them to each other. And so they made the smallest atom, hydrogen, the standard. And they said that, you know what? Hydrogen, you have a mass of 1 AMU. Atomic mass unit. It's a sort of fake unit. We're going to look at it shortly. So we have the relative mass scale, which has units of atomic mass units, and we have the absolute mass scale that has units of grams or kilograms as we know it. Now, what's the connection? Now, when you look at your periodic table, you see numbers. You see things like for magnesium, you see 24. For carbon, you see 12. And for hydrogen, you see 1 as the mass number. Now, what does that really mean? Now, the standard for the relative mass scale that was used in the beginning was hydrogen. Hydrogen being the smallest atom. It was given a mass of 1 AMU. Now, because carbon is 12 times as heavier as hydrogen, its mass was taken as 12, and magnesium 24 times as heavy as hydrogen, and so on, so it was given a mass of 24. So if we look at our periodic table and look at magnesium, we'll see that it has a mass number of 24. That's its relative mass, 24 AMU. Now, the mass number is also known as the relative atomic mass for magnesium. And the relative means that it's compared to a standard. Now remember, I told you that the standard originally was the hydrogen atom. Later, the standard used was the carbon-12 atom. So 1 AMU was described as 1/12 of a carbon-12 atom, 1/12 the mass of a carbon-12 atom. So relative atomic mass is the average mass of one atom of an element, okay, compared to 1/12 the mass of a carbon-12 atom. Now 1/12 the mass is basically 1 AMU. Now, let's try something out of curiosity. What would be the mass of 1 mole of magnesium? Let's try and find that out. What is the mass of 1 mole, or 6 times 10 to the 23 atoms of Mg? Okay? Now, 1 atom is 24 AMU. Now, 1 atom is 24 AMU. 1 atom of magnesium is 24 AMU. If I convert that AMU to grams and multiply by this number, since 1 AMU is 1.673 times 10 to the minus 24 grams. So now I have the mass of 1 atom, the real absolute mass of 1 atom of magnesium. So if I was going to try and weigh a magnesium, say there was a theoretical scale, this would be the mass that I would get, the absolute mass. Now, that's for 1 atom, and you can see that this is going to be a very small number. All right? But if I want to get 1 mole, the mass of 1 mole of magnesium, I would have to multiply that number over here by 1 mole of atoms, that is Avogadro's number. So 1 mole of Mg is going to weigh 24 times that number there times Avogadro's number. And when you multiply that out, surprise, surprise, what you're going to get is about 24 grams. The mass of 1 mole of magnesium, that is 6 times 10 to the 23 atoms of magnesium, is in actual fact 24 grams on a real scale. So, the relative mass is 24 AMU. The absolute mass of 1 mole is 24 grams. The two scales come together, brought together by this number, Avogadro's constant, L. And that's the usefulness of that number. It converts the relative mass scale to the absolute mass scale.